These notes are covering Newton's third law, the law of force pairs. Okay, so the key thing for Newton's third law is that forces always come in pairs, always. Okay, so one way that we can kind of demonstrate this very easily is by slapping the table. So when we slap a table, it actually slaps back. That's why your hand stings whenever you hit the countertop very hard. So you exert a force on the table, and the table exerts a force back on your hand, okay, because it's decelerating your hand. It's stopping it. So when you pull on the table pulls you towards it as well, okay? So depending on how strong of a table, or if it was like a countertop in your kitchen, when you pull on it, you can feel yourself move towards the actual countertop. Okay, and then when you push on a table, you're going to be pushed away from that object. Okay, so once again, forces always come in pairs. So every force is an interaction between two objects. Okay, so we have to have two objects acting upon each other in order for forces to be a thing. Okay, so as we slap the table, it's an interaction between the tabletop and your hand. Okay, and so each of them exert a force upon each other. So if we were just to tap lightly on the table compared to when we slap it, you can feel a difference in the reaction forces. Okay, so this just lets us know that there is a quantitative difference about the force of pairs. Okay, so if one increases, the other does too. So when we tap lightly on the table, okay, the amount of force that the table pushes back on us is proportional to when, if we slap the table, we apply more force, we get more force back on our hand, and that's why we kind of feel the sting of the force. Okay, so through experimentation, we found that the two forces in any force pair have the same strength. So the forces are going to have the same magnitude. They're just going to be in opposite directions, okay? And a key thing, too, is that if you remember whenever we talked about, like, adding force vectors, if we had these two forces, let's say that they're both 5 newtons, 5 newtons, okay? If we were to add those two vectors, it should mean that we get a net force of 0, okay? And if we have a net force of 0, that means that there's going to be no acceleration, right? There's going to be no change in the object's motion. Okay, so if that were the case, that would mean that nothing could ever move ever. Okay, so the key thing for Newton's third law is it's not acting on one single object. It's not like we have a box where we're pulling one way 5 newtons and one way 5 newtons, so it's not going to be moving. Okay, these are acting on two separate objects, and we'll kind of get to that once on this next page, talking about the free body diagrams of objects. Okay, so Newton's third law just states that every force is an interaction between two objects. Okay, so these forces come in pairs. And if an object exerts a force on a second object, then that second object is going to exert a force on that first object. Okay, and the key thing is that those forces have the same magnitude but in opposite directions. Okay, so we can see the interactions between two objects by drawing the free body diagrams for both of the objects. Okay, and then so these are the action-reaction forces that are acting with between the two objects. Okay, so if we have a 100 kilogram hockey player, okay, is going to check a 85 kilogram player, okay, and they're going to check them with a force of 65 newtons. So remember that when we draw the free body diagrams, the arrows point away from the object, okay? We're not going to point it towards the object. All right, so if this is player 1, this is player 2, okay? Player 1 hit player 2 with 65 newtons, okay? And the force that the player 1 is going to feel back is 65 newtons, okay? So this is going to be the action force, which is 65 newtons. This is going to be the reaction. Okay, because if player 1 is exerting the force, okay, that's the action force, and then the reaction is going to be feeling the push back from hitting that hockey player. Okay, all right, for the next one, you lean against a wall with a force of 25 newtons. So if we have our wall, and you have yourself, okay, if you lean on the wall with 25 newtons, that's going to be your action force, okay, and then the reaction force is going to be, it's going to push back in the opposite direction with the same amount of force. Okay. If you push against the ground as you walk, okay, so here's me again, and here is the ground, okay, you're going to push down on the ground. This is going to be your action force, and we're going to have an equal but opposite reaction force on your foot, basically. Okay, and then the last one, the earth pulls on the moon. Okay, so here we have the moon, okay, and it's pulled towards the earth. And then the moon pulls the earth towards it. Okay, so this is going to be the action force because the earth is pulling on the moon. The reaction is that the moon pulls on earth. Okay. So a lot of the time when we think about this, it's kind of hard to picture that, like the moon is pulling on the earth, or like we also feel gravity as well. So whenever we jump into the air, we could feel gravity working on us, pulling us back down to the earth. Okay, so the key thing with that is that we are pulling with the same amount of force back on earth. Okay. But the reason that we don't really see the earth moving, it's dependent on the size of the objects, okay, or the mass of the objects. Because if you remember, our equation is acceleration equals our force divided by our mass, okay? So if the force is remaining the same, right, because the action and reaction forces are the same magnitude, the mass, the depending mass, is going to cause the differences in acceleration. So because Earth's mass is so massive, we don't really see the acceleration, or the acceleration is so small that it's not really noticeable, okay? And we see this with other interactions too. If you think about shooting a gun, um, you can feel that recoil, okay? You can feel that backwards force that is applied to your shoulder, whatever it is, your hand. Um, that when the bullet leaves the gun, okay, that's the action force. We feel the reaction in the gun as it kicks backwards, okay? And so the acceleration of you and the gun is a lot slower than the acceleration of the bullet, okay, just due to the differences in mass.